All right, so in this video, we are going to take a look at standard enthalpy, which is really just more Hess's law calculations. So first off, standard enthalpy, which we'll know that we're dealing with standard when we see the little degree symbol there. That tells us that we are under standard thermodynamic conditions, which is 25 degrees Celsius. Just above room temperature. Room temperature is about 21 degrees Celsius, so a little bit warmer than room temperature. 1 atm of pressure and 1 molar solutions, because obviously if we have more concentrated solutions, then we would have a greater number of moles of our reactants present, so then there would also be a greater amount of heat that was transferred. So 25 degrees Celsius, 1 atm, 1 molar solutions, little degree symbol for standard. We will have reactions where you don't have things that are readily available, like single monatomic hydrogen atoms. So therefore, we have to use Hess's law in order to calculate. So if we take a look at this first one here, our target reaction is monatomic oxygen, which does not readily exist. Monatomic hydrogen also does not readily exist because both of them exist as diatomics, combine to make OH. And that is the delta H that we are trying to find. Then we are given what we will call reaction 1, reaction 2, and reaction 3. By manipulating them, we can come up with the delta H for that target reaction. So we use Hess's law. We just go through one thing at a time and then find the overall delta H. So monatomic oxygen exists in reaction number 2. So we are going to take a look at reaction number 2. We will have to flip it because monatomic oxygen is a product there. We need it to be a reactant. We also only want 1 mole, not 2. So we will need to flip it and divide it in half. So we will do O goes to 1/2 O2. Now the delta H for this, since we flipped our reaction, we need to flip the sign for delta H. So it would be negative 495. And since we cut it in half, we also need to cut the delta H in half. So then we would plug that into our calculator real quick, and that gives us negative 247.5 kilojoules. Okay, in order to get monatomic hydrogen, we will use reaction number 3. So monatomic hydrogen is a product in reaction number 3. We need it to be a reactant, so we will flip it. We also only want 1 mole, not 2 moles, so we will cut our reaction in half. So it will be H goes to 1/2 H2. Since I flipped the reaction, I have to flip the sign of delta H. So negative 435.9. I halved the coefficient, so I have to half the delta H. So if I put that into my calculator, I get negative 217.95. All right, lastly, I need to get OH. So OH shows up in reaction number 1. It shows up as a product in reaction 1, and we want it to be a product, so we don't have to flip our reaction, but we only want 1 mole, not 2, so we do have to cut our reaction in half. So it would be 1/2 O2 plus 1/2 H2 goes to 1 mole of OH. The delta H would stay positive because I did not flip it, but I did cut it in half. So I would divide my delta H by 2. So 77.9 divided by 2 would give me 38.95 positive. So if I take a look at, if I take a look at my overall reaction, the H, there should have been O2 there. The H2s would cancel, the O2s would cancel, leaving me with O plus H makes OH. In order to get the overall delta H, I would add up those three values. So negative 247.5 minus 217.95 plus 38.95. And that would give me negative 226.5 kilojoules as my answer. Now, that value makes sense because if I have an exothermic reaction, that means I am ending with less potential energy than I started with. So therefore, that is a key that my products are more stable. So the lower the potential energy, the more stable the products are. And OH is certainly going to be more stable than monatomic O and monatomic H. Those are not going to be stable substances. All right, now we just have a second example. So here is our target reaction. And then we have the three reactions below that we will manipulate in order to achieve that target reaction. So I just take one thing at a time. First thing, NO. Okay, reaction number one uses NO, and it's already a reactant, and it's already 1 mole, so I don't have to do anything to reaction one. I'm just going to rewrite it. So NO plus ozone makes NO2 and oxygen gas. I did not do anything to delta H, so I just recopy down the value of it. Okay, next thing I am trying to get is single monatomic O. So monatomic O exists in reaction 3. It is a product in reaction 3. I need it to be a reactant, so we're going to have to flip our reaction. Plus, we also will have to cut it in half because we only want 1 mole, not 2. So O goes to 1/2 O2. My new delta H, so it was 495. I flipped it. It would be negative 495 divided by 2. So 495 divided by 2 would give me negative 247.5 kilojoules. Okay, so I have NO, I have O, I even have NO2. So it might look like I am done because I have all three of my substances. However, if I sum up these two reactions, I would get NO plus O3 plus monatomic O equals NO2. O2, actually it would be 3/2 O2 because O2, O2, they would join together. That's not the target reaction that I was looking for. So I have some stuff that needs to get canceled out. Specifically, O3 and O2 needs to get canceled out. So that's reaction 2. So I need to cancel out O3. So therefore, O3 is going to need to be a reactant. So I'm going to have to flip the reaction. 3/2 O2 or 1.5 O2 would be the product. Now the O3 would cancel and the O2s would all cancel because I have a total of 3/2 on both sides. For the delta H, I flipped the reaction. So I have to flip the delta H. So positive 142.3. So in order to get my overall delta H for my target reaction, this plus this plus this. So we put those into our calculator, negative 198.9 minus 247.5 plus 142.3 gives us negative 304.1. Oh. Okay, there we go. So last example here, we have this as our target reaction. We are given reaction 1, reaction 2, reaction 3. So we need to get carbon as a reactant, so we will use reaction 2. We want 2 moles of carbon, not 1, so we will need to double our reaction. So we would do 2 carbon plus 2 O2 would make 2 CO2. My delta H would be negative 394 times 2 because I doubled my reaction. So 394 times 2 would give me 788. So negative 788 kilojoules. And that gets me carbon. Okay, now I need to get H2. So H2 shows up in reaction 3. So I'm going to use reaction 3. Now I only want 1 mole of H2. Reaction 3 has 1 mole of H2. And it's already a reactant, so I will not have to do anything to my delta H because I did not manipulate the reaction in any way. All right, now I need C2H2. So I'm going to use this top reaction because that top reaction uses C2H2. I am going to need to flip it because I need C2H2 to be a product and it's a reactant right now. So it would be 2 CO2 plus water goes to C2, H2, and 5 halves O2. So my delta H, I flipped it. It would be 1,300 kilojoules. I didn't change the coefficient, so I don't multiply by anything. So now I am going to combine my 3 reactions. So I would have the, let's see, what would cancel? I have a total of 2.5 O2s and 2.5 O2s. So those would cancel. The water would cancel on each side, and the carbon dioxide would cancel on each side. So that would leave me with the 2 carbons plus the hydrogen gas, making C2H2 in order to find the delta H of the overall reaction. I would just add up negative 788, negative 286, and 1,300. And that gives me positive 226. So this really was just more Hess's law calculations in order to find some standard enthalpy changes for some reactions that would be difficult to do in lab.